Another example, but before getting to the example, let's complete all the information that's required to express a pressure like this. Can you see? Okay. All the relationships, just in one piece, you should really always just kind of be able to refer to it. The next thing I want to do is take a look at the expressions UM, where they come from. Let me see, right. Just because I want to leave these on the board here, so. Okay, basically you have everything you need here. Okay. Except some approximations for large values, small values, asymptotic relationships. But, okay. Just one common mistake that's made is forgetting this sine theta here, okay? You see that this is forgotten. See, you're integrating, utilizing the orthogonality. And d eta is cosine theta, so d eta is sine theta times d theta. Just make sure that you don't forget. That's where it comes from. So, okay, so we have everything we need pretty much to solve any axisymmetric radiation problem from spherical sources. So why don't we try to solve one if you have a uniformly oscillating sphere, okay? Radiation from, not uniformly, from an oscillating sphere. Now, first of all, do you understand the problem? And you look like you do understand this problem. No. Let's talk about, do you understand the problem? What is the problem? Yes. Yes? No, describe it. No. You have a sphere, right? Okay. It's just oscillating back and forth, okay? And so you have a oscillates, let's say, with an amplitude. How would you describe, how would you express this as a boundary condition, the velocity of the surface? Because you need a boundary condition. What is this? That means you need to know the velocity of the surface. How would I write the velocity of the surface here? Well, give me numbers, names, letters.
It's like we wrote the pressure in the...
No. Tell me what to write. You write it down and you tell me. John? You know this stuff. See, we need to be able to express this. So what would be the pressure here? I mean, the surface velocity. And the first thing I want to do is, yes?
Can I tell?
Yeah, tell me.
Amplitude U times e to 2 minus I parentheses kx minus wt.
Omega t. But this is the velocity on the surface. What's x?
xa.
Sorry? A? What's x? What is x? Is it a coordinate, distance?
It's a coordinate. It should be... it should be r, I think.
Okay, well, we can make it r. It's easy. And then from here? So remember now, this is spherical coordinate. Spherical source. And we're saying you measured this velocity of this thing that's moving back and forth. And then you're giving me the velocity at distance, any distance r. Is that what you're doing? But that's not a boundary. That's particle velocity anywhere. So what is the velocity here? Do you know? You don't know. Because you haven't measured it. You know the velocity on the surface. We're starting from something that's going to radiate, that's moving. What should that be? And you have measured. Somebody gave you an accelerometer or some measurement device. You said, here's a ball that's moving back and forth. And you made measurements. What would it come out? It's moving at a constant amplitude. See, what would that be? Okay. Now, what kind of velocity are we looking at? Tangential velocity? This is a boundary condition that we want to utilize. So what does it have to be? You know the answer.
It's not tangential, but the radial.
Exactly. So we're interested in the radial velocity. Okay? And this radial velocity at the surface. And you made these measurements. This thing is moving at a constant amplitude like this. Okay? How will it change? How would you express this? How would you express this? Okay. You haven't seen this, so no. Let's say because it is moving in this direction, the velocity here is some amplitude, u1. Okay, or u0. We'll always have this constant amplitude. What's the radial velocity here? Emrullah, you're an expert on this. What's the radial velocity at this point? Imagine physically what's going on. Do you have the answer?
I have something in my mind. It's not.
Well, why don't you say so? What is it?
It's like in dynamics, the movement of the wheel. So we take 0 at the, but there's also no surface here.
Do you know?
Its magnitude must be the same, but it's not in the direction.
But what are we after? We're looking at the radial velocity. So my question is, what is the radial velocity at the top?
It's 0.
Exactly. Why is it so difficult? You're moving this way. See, there's no radial motion. There's nothing normal that's pushing up. Okay? And how about here? Now, think about this. The motion is back and forth here. And what you do is you take its component, because some part of it is moving up and down. Here, it doesn't have a component that's moving up and down, normal to the system. Okay? So here you do have that. So this variation of velocity, basically a cosine variation. Okay? So when somebody gives you, let me clean this just a little bit. So when somebody says radiation from oscillating sphere, you say find the radial velocity can be described as some amplitude times cosine minus I omega t. You can see how important it is that you describe the boundary condition correctly from the very beginning, and so you can solve the problem correctly. All right, so this is the description. You have the velocity, and you have all this information. What should the pressure be? Using this approach, what should be the pressure? Can you quickly try and see what you can come up with? What would be the next step? See, we cannot teach this class like this if there were 20 people. But because there are 3, I want you to learn how to solve the problems rather than just listening to me. Okay? So what is the next step here?
We can find AM.
Okay, AM. All right, to find AM, what do you need? You need, speak up. You need UM, okay? To get UM, what do? You take this integral, okay? Why don't we take that integral then? Because we need to find the coefficients. So if we go back and substitute here, say m plus 1/2. This is a simple boundary conditions. We know what the answer is, but it's good to practice to get to that point. 0 to pi. Now U8 theta is this. So let's put that U0 cosine theta. And PM cosine theta and sine theta d theta. Now, cosine theta is also P1 cosine theta, correct? Remember P0, etc. And if you look at here, then we'll have U0 m1/2 0 to pi p1 pm. Let's do this. Just simplifying and writing a different way. And this will give us looking at here, for all values of m other than 1, it's 0. So it's only valid for values of m equals 1. So we start from here, 1/2, and this portion will be 2 divided by 2 plus 1. Am I missing anything else? Okay. So you 0, 3 over 2 times 2 over 3. That seems to be, um is just the amplitude itself for m equals 1. Okay, and m is equal to 1. Now, we go back, we say A1 is equal to rho C U1. This is unfortunate. We should have just taken amplitude here because this can be confusing to you. Okay, let's say U sphere, U surface. Okay, otherwise, between, yeah. So this is M1, this is again surface here. U1 divided by B1. I delta 1 K A. That's our expression. Once again, for small values, we're again looking effectively for point sources. For small values of Ka, in this case, of course, this will be 3.5. So for small values of Ka, the expression for B1 can be approximated as 2 divided by Ka cube, and delta 1 is minus Ka cubed divided by 3 factorial. And if we substitute all of these into the pressure expression, you can see these. Okay. So this is a very small oscillating spherical source. Now, what about, once again, yeah, for small Ka? What about far field? What do you do in the far field? What would you do? Exactly. You look at the Hankel function and its values for Kr very large. Okay, so Hankel function then would be approximated by, let me write it here. It's always, of course, I omit these, but the first kind. And when we substitute, what do we see here that's a little bit different than the uniformly expanding one in the expression? The other one had this exponential component. It also had 1 over r component. We have something else that's different here. Okay? In fact, let me just express something. If you take this r and bring it here, we're just now doing a little exercise. Kr squared, oops, 1 over r, Kr squared. Okay, if you look at this term, let me just clean it up a little bit. Okay. If I just briefly do this, okay. When you look at this, there are, you see this 1 over Kr and I over K square R square. What we commonly refer to these as this is a far field term, and this is a near field term. Why is that? Think about Kr being about 10. Okay? Then 1 over Kr is about 0.1, but K square R square is 0.101. Okay. As opposed to if Kr is about 0.1. Kr is about 0.1. The far field term is approximately 10, and the near field term is approximately 100. Okay, so when you go to the far field, when Kr is very large, this becomes negligible. And that's why we call that the far field dominating term. And this is the opposite. And if you also note here, one of them is imaginary, the other one is real. Okay, so near field terms are where pressure disturbance is there, but the energy associated with them will not radiate to the far field. When you get the intensity and then follow the integration for sound power, this will not contribute to it. Okay, one. Let's see, there's something else I want to mention here. Oh yes, physically, what does this expression mean, particularly as compared to the uniformly vibrating source? So we said in the uniformly vibrating case, something that's pulsating. This is another term that's used, pulsating or uniformly vibrating. A small thing that's alive. Okay, just heart, actually. Think about a heart. It's just pulsating. And if you look at it from a far field at low frequency, that's what this is. Okay, so it goes. Now, if you have two of these side by side, before I get, yes. So at a distance r, we have pressure. We have this pressure expression, e to the I kr, kr, and so on. Okay, roughly. Now, when you have two of these side by side, small, but out of phase, plus and minus, then again, you're looking at the pressure. The pressure is coming from here and here. So you have, excuse me, plus and minus two forms. And the distance between them, sorry, if you look at these, let's say P plus has this e to the I kr plus and kr plus. And then you have the other one, e to the I minus kr minus. Okay. And so you have two of these arriving, and you're looking at them. Now, because the distance, let's assume that to be so small compared to the other one, these don't mean very much. Okay? And if they're of the same amplitude, they're the same, so we have PKR, but we have now KR plus. Phase is important. In fact, this problem, when it is solved, will give you this expression for very small radius. So what this is doing, see, the ball is moving back and forth, one side and the other side is out of phase. And that's, in fact, at the very small, Ka, very, very small, okay, 2 point sources, which we would call, in this case, a monopole, one pole, okay, and they become a dipole. Okay, and it's just 2 monopoles vibrating out of phase. And the radiation, if you look at these, can I have just your attention? Just 1 second. If you have both of these and you go straight up here, what would be the pressure? This and this, one giving one pulse, the other one is giving the opposite. Because in the line of symmetry, they add up, it comes to 0. So sound pressure in this line of symmetry is 0. Just like for this one. The expression here, if you look at cosine theta, this is the oscillation, okay, and theta is this angle. See, it's 0 in the line of symmetry. Similar that it's 0 in the line of symmetry between them. But it changes, of course, at other angles, and that change also comes from these differences and will give you the angle. The differences, I'm wondering whether I should not assign this to you as a little homework exercise to derive sound radiation from two monopoles that are vibrating out of phase. It's a textbook case. I'm sure you'll go and find it someplace, but I'd like you to exercise. So here's a homework. Derive sound pressure expression for two simple sources located distance d apart, uniformly oscillating under 80 degrees out of phase. Okay? Yeah. Okay, continuing on this. Now, I threw a lot of things at you here from one concept to the other one, but do you have any questions? You follow what we're talking about? We started with a radiation from a uniformly vibrating sphere, okay, and then derived the expression. Then we said if we make that small compared to wavelength and compared to distance, then it's what we call a point source. You know, you can take transformers that buzz, okay, at 60 hertz or 50 hertz here, or pumps, etc. At certain frequencies, you can treat them as a monopole, as a single, simple source, like a spherical source. It might have some angular distribution. Okay, so we started with this simple, uniformly vibrating source. And then we said, if its size is very, very small, then we can actually express it. We call it a point source. Now, what happens when you have an object that's moving back and forth? When it's moving to one side, it's compressing the air or the fluid on this side. But when you pull away from the other side, it's creating a rarefaction, pressure drop. Okay? So in some ways, you push here and you're pulling and back and forth. So that can be and is represented as a plus and a minus as two sources. Okay? And that is at very small scales, small size, small distance apart, is called a dipole source. Okay? In fact, tuning forks. You know what a tuning fork is? No? Music, the bing, right? A fork, okay, at different frequencies, right? I should have brought one to class. One side of a tuning fork is basically a dipole, okay, what you hear. And in fact, if you move your ear, or if you move it around your ear, its direction, you can tell that radiates better in certain areas than in other distances. You can tell this because it's just moving in particular direction. And there was, some time ago, there were electrostatic loudspeakers, very thin. I don't know if you have ever seen these yourselves. Loudspeakers like this, but very, very thin. Have you ever seen these? Okay. Yeah, these were very fashionable for a while. And what it is thin panel all the way inside. It's not like a cone. So electrostatically, you could move it back and forth. The reason for it at the time, the technology is, you needed large surfaces to generate low frequencies, the bass, okay? So you had these. But you can see here, it's like this, moving and radiating and so on. So when you put your ear just like this, very, very little sound. For the obvious reason, it's moving in this direction, back and forth. So maximum is either here or here, but nothing much here. And so that is a good example of a dipole type of radiation. All right? Any questions? The next example I have might be difficult for you, but it's again a simple one. So if you understand the methodology here, I think you should be able to do it. And let me explain what that is. First of all, let's go back. We have everything we need to solve these examples. Okay? That's what it is. The most important thing will be when I describe the problem, or when somebody describes the problem, you need to be able to express, looking up here, you need to be able to express the velocity distribution. So, let's clean up and say that we have a nice sphere of radius A, and we have a small point on it that's moving, just a small point. What will be the sound radiation? Now, physically, what would it represent? A number of different things, actually. It could be something like roughly sphere, but from one side, maybe a little pipe, exhaust, some sort of a sound coming through, just from one hole, tiny hole. So if you have a sphere, and let me see, something like this, and on it, you have something very, very small that has a surface velocity, constant amplitude surface velocity. How would you, first of all, model that or express that? And then, let me clean this, and then we apply everything on this, on the board here, all the information, to solve for sound pressure. See, when you do an engineering work, usually, whether it's a design or analysis, people don't give you equations or expressions. They tell you what the problem is. So radiation from a point source on a sphere. Okay, what is the expression? This is just one part is moving at a constant amplitude, just this. Okay, let's take a 5-minute break. I'll take the break. You try to figure this out. Okay? You sure?
Trying to express force on this point, like F0
Uh-huh. You can, but then that becomes an absolute point. And this has just a very small area. Yeah, just a very small. We call it, you're right, it's a point source. You can do that, and that will also give an answer. Yeah. But if you take it as a tiny little area, then you're able to use that size with respect to frequency, k times the area size dimension. And that's an important thing. So when I say point, it's always with reference to frequency, with reference to wavelength. Okay? When you use the delta function, then it's an absolute size. Okay? All right. 5 minutes.